So today's meeting is, we will have 2 lectures to wrap up all academic materials, and today's meeting will be primarily directed toward Joshua. He is a primary client, but I think it will be entertainment for everyone. And maybe the last 5 minutes of today and the whole meeting on Wednesday will be for Nate, Lola, and Adam. So it will be too late to incorporate the material of the Wednesday into your reports, but you still will be able to incorporate something from there into your presentations. So who did play with NMR facilities in wet lab? Anyone? Not yet? Maybe when you have organic chemistry lab or analytical NMR. Okay. So what do you get there? What do you get as a result of this practicing this instrument? What do you get out?
You put in a sample in a little vial thing and put it in the machine, and then you get the
chemical shift.
Yeah,
PPM?
like doublets and triplets and that kind of stuff.
Yeah. Okay. Yeah. Thank you. So the nuclei have magnetic moments, primarily protons, and by applying magnetic field, the energy of the spins up and down, quantum states up and down, split, but the amount of splitting does depend on local environment, whether this proton is near carbon, near oxygen, what solvent is around, is it interacting with nearby proton. And this splitting of energy is typically measured not in absolute values, but in relative values in respect to the value of magnetic field. And typically it's like parts per million ppm. And this approach, the splitting of the energy of spin in magnetic field, is a good feature to characterize structure of materials. Make sense? And this is kind of common knowledge of minimal common knowledge for NMR. In addition, there are more advanced techniques, not only splitting, but what is the word R in the MRI or NMR? Resonance. What is resonance? Joshua, you don't need to speak, but if you have an idea, just think how would you answer this question?
It's like where there are multiple like conformations kind of, and it's not really in any individual one, and it's kind of in a mix of.
Okay, you're correct as a chemist, but you are wrong as a physical chemist. So there is an ambiguity in the word resonance when you are taking like organic chemistry and you have like isomers which can convert to each other. They're called resonance. They have the same energy and they convert into each other, right? And in related to physical chemistry, resonance is similar in the sense that there is a match of energy. But in chemical resonance, there are 2 structures which have similar energies, right? And in physical chemistry and physics, resonance is typically when like electromagnetic radiation, oscillatory, the quantum of energy is in resonance with energy of transition in a molecule, like light and matter, right? So if they are objects of different nature, but they have the same energy. Make sense? So the resonance is a principle of any spectroscopy. If the electromagnetic radiation is in resonance with transition energies or energy offset between energies, then energy is absorbed or released. Okay, so now nuclear magnetic resonance or magnetic resonance imaging. What is resonance there? It's definitely not chemical structures of the same energy. Any ideas what is in the resonance? Well, do you have any direction of thinking? Nate? Let's just think together. I have slides which are impossible to show, especially after I'm being late, but better we just freely speak. So if we do have the energy levels of this spins in magnetic field, right? And the definition of resonance is making like light quantum in of the same energy as some transitions. What can you continue the idea?
Is it in resonance with the object it's coming into contact with? I don't really.
So
MRI, but I'm not sure.
So if one applies very strong magnetic field, then there are well-defined energies of the those protons which have spin up, and those protons that will have spin up, they will have different energies. And even the same proton, when it flips the spin, it will be two different energy levels. Is it possible to send a quantum of light or electromagnetic radiation of this transition energy that will induce the flip of the spin?
Yeah.
Okay. Makes sense? So the resonance means that there is a oscillating transversal magnetic field that flips the spin in this NMR sample. And Joshua hopefully will teach us more in his 4 or 5 minutes presentation on Friday. I'm trying to just provide background for his talk right now. So last thing that we finished on Wednesday before grading of the papers was the dictionary, and maybe it was typed a little bit better, but it was the same one. So we made this hocus pocus with spin flip and introduced quantum operators, right? And there are ladder operators that makes transition up, down, and then product of the ladder operators, which just measures whether it is up or down, right? Both in Dirac notation and in the matrices. For NMR and MRI, it is critically important to combine those ladder operators in form of Sx and Sy, which will correspond to observables of the magnetic field. So this alternative definition of S plus as summation of X and Y is a literal analogy with defining creation and annihilation operators for harmonic oscillator as position and momentum. So Sx is analog of position, Sy analog of momentum in mathematical sense. Their real world implementations are just magnetizations in different directions, but mathematically they behave in a similar way. We will see that they will rotate, and by adding them together in a sense of operators, they will create operator that makes transition up and down. Okay. So if we have this 3 components of each spin and add them together and multiply by a constant, it will be magnetization of material, something that can be measured, like taking a compass and walking around head of the patient, which is wrong, right? It is something much more sensitive than the compass. And what is important that in it's quite ugly drawing, but you will see it in the slides and in any materials about NMR and MRI, that there are 2 magnetic fields. One is B naught, sometimes called parallel, and another B1 or like BX, BY as a function of T transversal. So large parallel field creates splitting between different spin states, and it is different offset, different splitting is what Wyatt observed in analytical chemistry NMR signal, ppm. And the Bx is transversal field that may induce transition of the spin as a quantum system between different energetical states. And what we will speak in the remaining time today, and what Joshua will present on his presentation, his project, is what happens to spins that are excited by this transversal field. What are their quantum states? So I will do all efforts to re-arrive to the same slide again by showing a few more slides. So it is kind of a expected outcome. So the presentation of Joshua will be about a traveler going on the equatorial line of a sphere, of a globe. And the meaning of this figure is the precession of magnetization, which happens in this NMR MRI single spin 1/2. So we need to discuss as much as possible in this limited time, what is this circular motion, what is the sphere, what are Sx, Sy, and Z, how they are connected to definition of this two-level system and to quantum operators. So in a similarity to harmonic oscillator, the summation of plus and minus correction and annihilation gives projection Sx, which is analogous to position. The subtraction with divided by imaginary gives Y projection, orthogonal to it, of magnetization. And the subtraction of the products, up, down, down, up, gives Sz, which is related to energy. Same as in harmonic oscillator, A dagger A gives energy of harmonic oscillator, right? Here, similar combination, S plus, S minus, plus minus conjugated thing gives energy of magnetic system. And if we do not change, if you do not irradiate the system by external pulses, if you just let it go on its free rotation, free precession, then Z component doesn't change and X and Y behave like sine and cosine, where frequency of their oscillations depend on the offset of energies for the spin up and spin down state. Those that Wyatt observed in analytical as ppm peaks. Okay. So we are going to see that the sine and cosine projections will correspond to circular motion. Yes? Okay. So Joshua will explore a figure of this style, and it's his. I do not want to take his piece of bread of explaining what it is, but just providing definitions which he may redefine later. So this style of figure shows the length of the vector connecting the center of the globe with position on the sphere. Here, and in today's lecture, we will consider that the length of this vector is constant. But Joshua will show something unusual when the length of this vector is changing. So summation together Sx, Sy, Sz can decline. So there are some mechanisms for decline and then for reappearance. This is something really exotic and going beyond the scope of the class materials. Therefore, it is a project. And I still admire Joshua as taking this advanced complicated subject. But the length of this vector is head of squares of these magnetic projections, or if Z projection is not changing, we can speak about polarization, which will be only X and Y. Should be X here. So goal of our meeting is to speak what is Sx, Sy, Z, and why they're changing in time. So this is demonstration of this exotic thing when the several individual molecules in a sample give different contributions to signal, and when this xy from individual molecules are directed in opposite directions, then the overall lengths can be smaller. Make sense? Okay. Here are definitions of spin operators. If you are scared of physical chemistry, by this class, you will never see them again. If you are not, and if you continue graduate education in this direction, or elect to take some advanced courses, you will see those guys again. So if we describe spin as a particle with two basis states, projection up, projection down, then real world observables are connected to this wave function through these three operators, X, Y, and Z. So here there is off diagonal part of the matrix, and they have the same sign. Off diagonal, they have different and they imaginary, and Z is like energy. It's on the diagonal with plus and minus. And in this matrix notation, one can see that this arrangement can be obtained by adding together raising and lowering operators, which are just one element in the square matrix, right? So adding these two matrices will result in this matrix. And here is the transition from plus and minus, raising and lowering to Sx. Same transitions are possible for Sy and Sz. And if we are looking onto expectation values of this, I'm just trying to be blind drawing because this screen by some reason is not working. So if you look on the expectation values instead of operators, then we can set up a vector that defines the state of the quantum system. If it is completely in the up state, it will correspond to North Pole. If it is completely in down state, it is in the South Pole. And if it is halfway between up and down, it will be on the equatorial for pure states that are described in this course. The average over ensemble, when the length is shorter, appears only after summation over multiple molecules. And it is beyond the scope of this course, but it comes through destructive interference. Okay. So resonance, magnetic resonance, is when one sends a quantum of electromagnetic radiation onto the energy of the offset between the spin up and spin down states. But this energy belongs to radio frequency. It's not like UV, visible, or infrared. It's much lower. So here is a figure from textbook. So parallel field creates splitting. The bigger parallel field, the bigger the splitting. Transversal field creates transitions between up and down. So if we want to convert spin down into spin up, we can send a pulse to irradiate it with transversal radiation. Or if we do halfway, if the amplitude and duration of the transversal electromagnetic signal is weak, we can create a superpositional state. So Sx squared, Sy squared is the magnetic polarization, which is a measure whether this single proton is able to absorb or emit electromagnetic radiation. And it is a main observable in the work of Joshua. So from now on, I'm going to invest time in showing boring equations, and I almost got lost in them while reviewing the slides. So I would be not surprised if anyone or everyone in class get lost too. So just brief navigation map, what I'm going to do. So you are 3 lectures away from becoming certified physical chemists and quantum theorists. So you are already equipped with a lot of theories and methods. And one of your favorite, hopefully, theories is Heisenberg equation of motion, where one can predict an expectation value of real world observable without dealing with wave function, right? By making the commutation of the operator of this observable with Hamiltonian. So if we do need the projection, magnetic projection Sx, we can either do Heisenberg equation of motion directly for it, or independently for each component S plus and S minus. So if we set up Heisenberg equation of motion for S plus, S minus, solve it, plug it into this definition, then we will get how the magnetic projection Sx depends on time, right? More or less. And then we can put minus here, imaginary unit here, and then it will be a way to project magnetic component Y, right? Okay. Start, set, and then we will combine them together and get polarization. So no, this slide is connection between spins and Nate. You may and Lola and Adam. So it is something I will speak later. So concept of two-level system can be transferred from spin to what you guys are doing mathematically, but I'm just giving heads up. Okay, to practice this equation of motion, we set up Hamiltonian as projector alpha, energy alpha, projector beta, energy beta, and then if we acting by Hamiltonian on the S minus operator is beta alpha, then one can practice bra and cat things as we did for again and again for harmonic operator, and find that alpha times beta convolution gives 0, and here alpha times alpha gives 1. And then we will see that from these two terms we keep only 1 e sub alpha, and there is one more beta from here. And then we recognize that by acting on the with Hamiltonian of this spin system onto raising operator, we are getting raising operator back with energy of spin up. If we apply it again in the opposite order, raising operator and then Hamiltonian, we again will practice this Bryan-Cat machinery, and we will see that the first term is declined because we convolute beta and alpha, right? It gets to 0. And then second term, when we convolute beta and beta, it will be 1. And then when we process it, we see that it will be again operator, raising operator S plus, but with different energy. So depending by the order of these operators, we will pick different energies from the Hamiltonian. And those energies, alpha and beta, right now I'm skipping it, but actually it will be value of magnetic field times the value of spin. So magnetic field times 1/2 up, magnetic field times 1/2 down. So if we merge these things together, we will notice that commutation of the Hamiltonian with raising operator is raising operator times energy offset between the states. And if you plug into the equation of motion, we'll see that one can integrate this as differential equation, right? So unknown function time derivative equals unknown function times constant. So we divide left and right by unknown function, ds plus divided by s plus equals to constant times dt. And then we integrate and see that log s plus is a linear function. Or if you put it into the power of exponential, we see that s plus evolves in time as its initial value times exponential evolution, right? So the same trick can be applied for S minus. And the difference will be only that the evolution will be in the opposite direction. So alpha minus beta, beta minus alpha. And if we add together, add or subtract these two solutions for plus and for minus, then by adding together exponentials rotating in different directions, we get cosine by Euler, right? By subtracting, we're getting sine also by Euler. And by practicing adding or subtracting these things together, we will get as cosine and sine. So the Sx magnetic projection will oscillate as cosine, and the Sy will oscillate as sine. So if we follow like time 0 cosine maximum, sine is 0. Time increases, the x projection gets smaller, y projection increases. And if you continue, it will be an equation of circle. So it will correspond to the vector pointing different a trajectory, circular trajectory on the equatorial plane. 6 minutes more. I think we are doing good. So the energies are plus and minus projection of field Z with some constants. And it is something that one can find either in textbooks or if you ever take physical chemistry or quantum mechanics, it will be likely problems to be solved and get this answer. So next thing is much heavier, and it is please enjoy it if you can, but it's primarily for Joshua. So we were speaking about in the language of expectation values of operators and wave functions that we skipped. If we define wave function for two components, it will be a vector of two numbers, C1, C2, or C alpha, C beta. And they will evolve in time in quite simple differential equations, which originate from Schrödinger equation. But to deal with spin projections and change of the length, average, dealing with average of ensemble, now we need to take another, your another favorite tool, density matrix, when one multiplies components of wave function to itself. So if the wave function is 2 by 2, the matrix will be, if wave function has two components, any operator matrix element and density matrix will have 2 by 2, 4, right? So 4 components, 1, 1, 2, 2, 1, 2, 2, 1. And one can set up the equation of motion for each of them just by connecting the equation of motion for expansion coefficients, and here thing is unchanged. So these are equations of motion for 4 elements of density matrix. If one names them as 1, 1, 2, 2, 1, 1, 2, 2, then the density matrix will evolve in time, will obey differential equation where the time derivative of these elements equal to themselves multiplied by super operator that includes anything that can happen to it. So Joshua, you mentioned initial values in your report telling like 1, 0, 0, 0. So it corresponds to initial value problem for this equation of motion for density matrix. So rho 1, 1 equals 1 and others equals 0. So this equation can be relatively easily converted into equation of motion for spin projections. So the combinations of elements of density matrix naturally give expectation values of spin of magnetic projections. And if one does this transformation, then one can set up equation of motion for projections x, y, and z, which will depend on the values of s, x, y, and z at the same instant of time. So it still be linear equation of motion. And changing in time of this system of three differential equations will correspond to motion on the sphere. If we have ensemble with different offsets, with different chemical shifts, then the frequency with which phase oscillates is changing. And by adding together signals from different spins, we'll give some exotic signals. So then the projections upon average will lose its amplitude. So if one has several signals, for one signal, we change occupation of ground state goes to 0, excited goes to 1, off-diagonal elements appear and disappear. But if one repeats the same simulation with different, just a second, it was a pi pulse. If you do halfway, then originally excited goes to 50%, originally empty goes to also 50%, and off-diagonal element dashed becomes also 1/2. So it will be equatorial. But if we slightly change chemical shift, slightly change environment, it will go a little lower or higher, and the off-diagonal elements start oscillate. But each of them will oscillate with its own slightly different frequency. And if you add together all these colorful lines, then the average line will show a decline. So this decline is what Joshua is going to explain us, but I'm skipping the second part, which is even more interesting. 50 minutes. Okay, done with lecture. Quick comment to Nate. The namings for quantum states of heavy atoms is additional challenge that is resolved because they have angular momentum from their rotation and from spin. And for your iodine molecule, it's quite heavy. Typically, one uses Russell-Sanders terms, which include angular momentum, spin multiplicity, and summation or subtraction of angular and spin. And if one looks onto iodine with this Aufbau with only one unpaired 5p electron, then its angular momentum will correspond to only this spin because those are paired. So it will be just one, right? And spin will be 1/2. So we for spin 1/2 multiplicity 2s plus 1 equals to doublet. Subtraction of orbital and spin 1 minus 1/2 will be 1/2. And then the symbol for ground state of single iodine atom will be 2p doublet. P for angular p, like SPD. If you read literature on iodine compounds, you will see these notations, or you might have seen it before. Okay. And here, what we are going to do on Wednesday, we are going to obtain absorption spectrum, which complements work of Lowell. Lowell computes emission. On Wednesday, we all consider absorption because of the quantum states in the potential energy surfaces for ground and excited states. So there are several lines. Here is absorption spectrum, and lines in this spectrum should be interpreted this way. First line, transition from here to there. Then second line, from here to there. So here are different transition energies, and the intensities of this transition based on the overlap of the pink and blue vibronic functions. Okay, enough. Thank you for your attention. Looking forward to see you on Wednesday and your updated works right now during the day. I'll stay here and answer any questions, but if you need to depart, feel free to do so. Thanks again for waiting and not departing before my arrival.